What can I say after all this? As you know, I always keep to the time of my lecture. And but I really didn't plan on saying very much. I know that Eliezer asked me to summarize the conference or this part of the conference, but it's really impossible to do so. I really enjoyed the last 2 days. They were wonderful. It's a wide range of topics, and so much more is to come in the next 3 days that I'm looking forward to. So I don't want to summarize. I do want to thank everybody. Let me do that before I go on to a few remarks. We could cut this out. Raise the... So I do want to thank everybody again, all of you who came from far for this. I'm extremely flattered and touched, and for all of you who worked so hard on making this all possible. Sorry? I know Ofer. And Eliezer. And many others. And Michal. And so it's been very touching. Yesterday was beautiful, and today was wonderful, and it's fantastic. And I'm looking forward to the next 3 days. Eliezer stole a bit of my show, in a way, because since I don't have anything really, I didn't want to give a physics talk, I thought I would talk about questions. Now, Eliezer had a twist. I like to do that. I also like to make predictions, and so Eliezer, merged both of those likes together, questions that are predictions, and Ofer took notes. So everybody's going to be held accountable at my 90th birthday. But questions are really, the Eliezer quote, I'll come back at the end to that millennium, but at that point, it was really Mike Duff's idea to come up with questions for the 21st century or for the next millennium. And I think it's very important because our life as scientists is totally shaped by the questions we ask. And now many of them are questions, and they're really questions that belong to the community as a whole. And I've always thought that, when I finally retire and have time, I'll write a history of science as a history of questions. How have questions evolved over the years? And so I like sometimes to go back and think, what questions were we asking 45 years ago? And they really are totally different than the questions we're asking today. And those of you who've heard me give public lectures know that I often like to end with a discussion of questions that Eliezer didn't ask, which is a very interesting one. Is there a final theory? To some, and I'm an agnostic on that subject, and I explain to people that I have a mathematical model of the universe of knowledge, which is a multidimensional manifold, and it's what I call the sea of ignorance, and we live within the sea of ignorance in a what always becomes a simply connected domain of knowledge, and that expands out into the sea of ignorance, and that I like this model, especially compared to the onion model, where you dig inwards to the core of the onion. That doesn't work. But this one explains how knowledge, the volume of this, domain that we're trying to expand, grows. Certainly has grown enormously over the last 1,000 years, even the last 45 years. But on the other hand, the area, the visible ignorance, the knowable unknowns, which is what we call ignorance, is really the surface of this volume of knowledge, because we're only aware of questions which are at the border between what we know and what we can perceive we don't know. So much like the exploration of the earth was an expanding area, and if you look at old maps, you'll see that near the boundaries of what people had already mapped, they were sort of clearly aware that there was something just beyond that, but they didn't know how beyond that. It's just all question marks. So knowledge increases like the volume, and ignorance increases like the area. Always increases. We always have more questions, and we always feel, oh my God, we've learned so much, but there's so much more to know. And yet we feel wiser because, as you know, volume increases faster than area. Well, no, it isn't a fractal. So look, this mathematical model can be expanded in many, many ways. And we know very well the surface isn't a fractal. There are effects, namely lots of people working, smoothing out the boundary all the time. And whenever there's a new island of knowledge, someplace which is disconnected, a lot of people work to connect it so it's simply connected. It also has rather trivial holonomy. But anyway, the question then is whether this is compact or non-compact. Obviously, if it's compact, there would be a theory of everything. If it's non-compact, we can go on forever. I'm totally agnostic. The world is so far flat. But that's a pity, because one of the tragedies of life, especially being a scientist, is as you approach the singularity, as Francois said, you realize that you're not going to get an answer to all these questions. So when you're young, you ask all these questions, and you cannot imagine what the answers might be. I mean, 50 years ago, questions we were asking seemed impossible. I mean, could we understand all these particles and how they interacted and what the weak interactions were and what the strong interactions were? If you had asked that question, done a survey like you did today, 45 years ago, 1971, there's no question in my mind that the audience would have never dreamed that it would all be over in 10 years. Never dreamed, and nobody would have been optimistic that it would all be over. And so that's a great pleasure. One of our great pleasures as scientists is realizing some of these dreams and answering some of these questions and making either substantial or very small progress, depending on how big this universe of knowledge is. But then the tragedy is that you know that there are going to be all these questions that are not going to be answered. So I tried to come up with some questions I would like to see answered, and I don't know the answers. And they're not as, well, they're somewhat similar to questions you asked. So some of them have to do with QCD, which I must say is my first truly deep love. And I would like to see, even though John tried to claim that QCD in a box is proved to exist, not exactly, but I'd really like to see it established rigorously, although we all know that's not necessary. I would like to see the hydrogen atom of quantum field theory, n equals 4, supergravity, a close cousin of QCD, a kissing cousin of QCD, solved, at least in the large n limit. We're very close to that. It will be done in 15 years, I have no doubt. But I'd really like to see people already starting to expand that out, because, you know, the solution will be quite more and more explicit in the next few years, and then we should start doing 1 over n corrections and expanding integrability, deforming integrability, and breaking supersymmetry, and trying to use that analytic to learn something about the real world. It would also be nice, by the way, to understand the 6-dimensional little string theory, which presumably is the mother of the hydrogen atom. It would also be nice to have other analytic tools for discussing for understanding QCD beyond lattice gauge theory, which is a really crude but incredibly wonderful calculational tool, but one that doesn't allow us to ask time-dependent questions, calculate scattering amplitudes, then explore new phases of quark and gluon matter. And there's some hope. Some of these new techniques that are being developed in condensed matter physics, tensor networks and the like, should give tools that could perhaps be used for time-dependent phenomena. And then there's perhaps the revival, which I'm quite fascinated by, of semi-classical techniques, the idea of making sense out of all the knowledge of all semi-classical saddle points of a quantum mechanical system to recover the full quantum mechanical system, what's called resurgence, which is being pursued nowadays. So there are a lot of questions about the real world, about QCD, which will be here for centuries, will be studied as mathematical physics, but still as real physics, about which there are still things we don't even know experimentally. There's much to be done, and I would love to see that in the next 15 years. As far as particle physics goes, the three things, the three big questions in my mind for the last 30 years have been what Eliezer has already polled the audience on. I was a bit shocked to hear the pessimism about supersymmetry. And again, I'd like to remind the younger people here that, sometimes the simplest scenarios seem doom, 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 and then suddenly, for example, consider the Higgs mechanism and what we've gone through in the last, Francois, 50 years. It could have been much more complicated. I would be interesting to have asked this audience, same audience, what they would have thought 5 years ago. I bet you, okay, if we could, I could do the experiment. If you're really honest, well, I won't. But if you're really honest, what this audience would have said 5 years ago, I am sure that at least half the audience would have been extremely doubtful that such a simple perturbative description of spontaneous symmetry break in an electroweak sector would have been discovered at the LHC. Do people disagree strongly? Sorry? No, it's enormously problematic, as you know, for many reasons, and a good part of 20 years ago, half the audience would have said, of course, it's problematic, and it's obviously technical. Any case. So I'm still optimistic that supersymmetry, compelling solution to many problems, will appear at the LHC. I'll remain optimistic until proven otherwise and having to pay off various bets. Dark matter will certainly, I am sure, be answered, at least to the extent that we'll realize that we better in the next 10 to 15 years. It could be a modification of gravity. That would be enormously exciting. We're not going to decide that experimentally. It's hard to imagine unless people who try to modify gravity make predictions that could be tested.
David, are you saying you're confident we'll find experimental evidence for the dark matter particle?
I'm pretty confident, yes. I'll take even odds on that. But the thing that I really, would like to know more than anything is how the forces are unified. Because, again, after the standard model, we had no right to expect that within a few years, after Edouard came to Princeton, or 45 years ago, that it would all be over within a few years. But I had no right to expect that it would all be so simply connected, that everything would fit together in 3 gauge groups that naturally fit together in SU5 or SO10 or E6, and that that we didn't need any more matter than had already been discovered, except for a right-handed neutrino. And it's absolutely compelling in the unification of the couplings at around the Planck scale. So we all believe in unification. If you hadn't polled we could poll the audience again. I really doubt whether there'd be many people who don't believe that the forces we observe in nature aren't unified, probably with gravity. But what little progress we've made on being able to turn that into a predictive and tool, or an explanatory tool of parts of the standard model that we can't calculate, is a bit depressing. And I certainly that's in the standard list of particle physics questions, the one I would really like to know the answer to. Then there's string theory, my second big love. It's amazing to come to string theory and field theory. I argue this conference is entitled String/Field Theory, are clearly part and parcel of the same set of ideas, the same framework. But what always is striking me more and more at string meetings like this is how little string theory there is. And whatever it is how little string theory in the old-fashioned sense there really is. Most, and some of my younger string theory colleagues, I'm not sure, well, I might think that string theory is ADS-CFT, which is a beautiful part of the framework, of course. But I still would like to know whether there is a non-perturbative formulation of string theory as a theory of strings and perturbative strings, the completion of that, a theory, a non-perturbative definition of quantum gravity, which isn't just defined in terms of duality with quantum field theories. I would still like to know simple, you would think, questions about string theory and the theories we have enormous confidence in, like mathematical models, like string theory in flat 10-dimensional space-time, which because of dualities we believe has no problems anywhere. And there are many physical questions we can't answer. The one that I would really like to have resolved is the so-called post-selected exclusive string scattering amplitudes, or exclusive string scattering amplitudes at finite angles, something which Paul Mendy, who's here, and I showed that in perturbation theory has incredible simplicities that haven't been understood. But what is the answer? Something we should be able to calculate, and not necessarily without perhaps having to really understand the quantum nature of black holes if we stick to finite angles. And then there's the symmetries of string theory. What's underlying string theory? We've heard a lot about various ideas about higher dimensional symmetries, higher symmetries, E7 to E10, mostly from the field theoretic point of view. But surely there's something in string theory that defines it in terms of its underlying algebra or symmetries, which we don't understand. There's string field theory, which I spent too much time on, and hasn't yielded anything really substantial. And maybe probably the wrong approach, but what is the right approach? Or is there really none? Is it always, do we have to go back and construct space-time and string theory from a dual quantum mechanical system. And then that's, of course, related to emergent space-time. These are questions which I doubt will truly be answered in the next 15 years. They're really tough. And finally, the toughest of all have to do with cosmology, the Sitter space, the cosmological constant, or just in general, the whole issue that we have to face up to of if there is a solution to all of these questions, in which, such as unification, that involves gravity, then we're dealing with quantum gravity, and then the solution, by definition, is a space-time. And by definition, being a space-time has to deal with the beginning and the end. If we lived in an equilibrium state and we didn't have a thermodynamic arrow of time, I think we would recognize, well, we wouldn't exist. We are objects, collections of particles or whatever, that our very existence involves a direction of time, the arrow of time. And so we think it's natural to formulate physics as predicting the future given the present or given the past. But that's not evident in the law of physics. And if we're going to have a theory, a unified theory involving quantum gravity, the answer obviously has to say something about what the beginning was, what the initial state was, what the initial conditions were, what picks out a particular solution, or whatever. We don't know the rules, but equally well the end. And here, I truly believe we have no idea what to do. We're playing around. All of that is good, but I can't imagine this being resolved in the next 15 years. At that conference, we challenged people. Ed and Michael Duff and I formed a committee. We challenged people to come up with questions that would survive a millennium, not just 15 years. So I phrased my question very carefully. And the way I put it, Eliezer didn't remember, was that, there's supposedly if you're a good physicist, after you die, you get to ask God one question. Just one. So I thought about it that way. I said, what question would I ask God? And so I asked, are all dimensionless parameters, all measurable dimensionless parameters, calculable in principle, or are some determined by environmental or quantum mechanical accident and uncalculable? That was the first question there. Now, I truly would like to believe that the answer is yes. Because the greatest joy for me as a physicist is to calculate some number that can be measured with arbitrary precision. And to some extent, I've been lucky. Not I don't do the calculations, but at least I contributed to the calculation of the mass ratios of those hadrons that were being discovered when I was a graduate student. Enormously pleasing. Nothing can be better, at least from my point of view. So I would like Einstein to believe that that's how nature is constituted, that all those dimensionless parameters that could be measured and are being measured by experimentalists could in principle be calculated. There are people who believe otherwise, and it's become quite popular. But I'm not going to ask God that question just to get a yes or no answer. The whole point of that question was, for God at least, was that if he says, as I expect he would, if she said, yes, then he has to explain it. And of course, to explain it, he would have to answer all the other questions that I have or that I haven't yet thought of. Thank you.